Okay, the last thing I'd like to give you an example of for node voltage analysis is something called a supernode, which always makes me think of Super Grover from Sesame Street. So, we're going to look at this circuit, and you can see that we have a couple of current sources. We have a reference node on the bottom, and then we have two nodes, V1 and V2. Now, you'll notice I did not put our reference node right at the bottom of our voltage source, okay? In this case, we can solve this, but we need to use something called a supernode. So one thing we can kind of say is that our voltage source is floating because it's not connected to the ground, okay? Because of that, we can't just go and say, well, okay, well, V1 is obviously this and V2 is obviously this, right? And we can't use the current sources to determine the voltage directly because we don't know, there's no assigned property as far as what kind of voltage drop we have to see across a current source, okay? So, it looks kind of like a hopeless situation until we realize that we have to apply something called a supernode. And what we're going to do is we're going to do KCL, but we're going to do KCL for this here. We're basically going to group these together as one single node, and we're going to solve our our KCL equations treating all of the currents that are coming into both V1 and V2 in one single equation. And the reason we can do that is because we get one other equation. We know that V1 has to be equal to V2 plus 6 volts. So this gives us our first equation, okay? We have a relationship between V1 and V2. So that gives us one of our equations. Now we can make the other equation. But what we're going to do is we're going to look at all of the currents that are going into and out of V1 and V2, okay? So, again, I'm going to treat everything as if it's going into our supernode. So I'm going to start out and say that 6 milliamps is going into the supernode. So that's our first current, okay? Now we've got a current that's going from ground, a reference node, into V1 through a 6 kilo ohm resistor. So I'm going to say plus 0 minus V1 over 6 kiloohms. Okay. Now I'm going to keep writing my equation because we're treating this as one big node. So now I've got 0 minus V2 over 12 kiloohms. Okay. And then we have coming out of V2, so I'm going to treat it as negative, 4 milliamps. Okay. And that all has to be equal to 0. Okay, so I'm going to combine some terms here. So I'm going to have minus V1 over 6 kiloohms minus V2 over 12 kiloohms. If I add my currents together, that gives me 2 milliamps on the left-hand side. When I move it over, that ends up being minus 2 milliamps. So I'm going to get rid of all my negatives, multiply everything times negative 1. The other thing I'm going to do, just because, you know, I like to do this, is say that I'm going to multiply everything times 12 kiloohms. That's going to give me 2V1 plus V2. 12 kiloohms times 2 milliamps is going to give me 24 volts. Okay, now I have one equation here and a second equation here, right? So I can plug V1 in from my first equation into my second equation. So I'm going to have 2 times V1. Well, V1 for my first equation is V2 plus 6 volts plus V2, and that has to be equal to 24 volts. So multiply this out. That's going to give me 2V2 plus 12 volts plus V2 equals 24 volts. I add up my V2s. I end up with 3V2. And then I subtract 12 volts from the other side. That gives me 12 volts. That means that V2 has to be equal to 4 volts. All right. And then V1 we can find just using equation 1. V2 plus 6 volts, well, that's just going to be 10 volts. Okay, so now we have the voltage for both of those points, despite the fact that we didn't hook the voltage to ground. And the way we do that is, again, using the concept